Hey, what's up, guys? Back at you here with day 45. We're looking at something different today. We're looking at a very important theorem called the mean value theorem. The mean value theorem is pretty important in calculus, and we'll just take a look at what it looks like here. I'm going to start with the definition, and then I'm definitely going to take some time to kind of explain what that definition means. So here's the definition. It's a little bit wordy, so if you need to pause the video to write it all down, that's fine. Go ahead and do this. Here's my definition. So what it says is, if a function f is differentiable on the open interval ab and continuous on the closed interval ab, then there must be a point c where a is less than c is less than b, such that f prime of c equals f of b minus f of a over b minus a. So again, pause the video here for a second, and let's go ahead and just write that definition down, and we'll explain it a little bit more here in a second. Okay, we're back. Let's take a look at this definition and see how this is going to play out. So the first thing we can see here from our definition is that to use this theorem, we need to show that f is a differentiable function. Okay? This is different than the conditions needed for intermediate value theorem, the IVT. For the IVT, you needed to, all we needed was f to be continuous. This is a little bit stricter of a qualifier here. We need differentiability on AB and continuity. Don't get too hung up on the details of why is differentiability an open interval and continuity a closed interval. To go into that is a little bit more of a detailed conversation. But the most important thing that we get from here is, if we know a function is differentiable, then we know that there must be some point in between a and b where f prime of c equals that f of b minus f of a over b minus a. Now that f of b minus f of a over b minus a is our same, that was our same quotient for average rate of change. So just as a reminder, this f of b minus f of a over b minus a, first off, that is just the slope of the line connecting 2 points, x values a and b. Okay? This is also our average rate of change. So what the mean value theorem is saying is there must be one point where the instantaneous rate of change, right? A derivative is an instantaneous rate of change. There must be some point in there, at least one, there might be infinite, but there needs to be at least one point where the instantaneous rate of change matches the average rate of change. So let's take a look at this. I think it's easiest to look at it in graph. So I'm just going to put a little graph in here. So I'm just going to sketch a graph of a function that needs to be differentiable. So that, again, differentiable means that it's connected and smooth. So something like this. Okay. I'm going to put A right here and B right here. Okay? So what we have is we have 2 points, the two endpoints on this section from A to B. One of them is right here. That is the point A, comma, f of A. And our other point is up here at B, comma, f of B. I'm going to focus on the right side of our mean value theorem equation first. The right side of the equation says f of b minus f of a over b minus a. Well, we know that that's just the change in y over the change in x, or the slope, right? So the slope of the line that connects those 2 points, I'll use a different color here. This slope equals f of b minus f of a over b minus a. Okay. So that's the slope of what is the secant line there. That's the average rate of change, right? Now, since this function is curved, its rate of change is constantly changing throughout that whole interval from a to b. But its average rate of change, right, the average derivative there would be f of b minus f of a over b minus a, whatever that slope of that secant line is. What the mean value theorem says is as long as a function is differentiable, right, which the sketch I drew is, there's got to be some point C in between A and B where the instantaneous, right, the slope of the tangent line matches the slope of the secant line. So somewhere in here, I'll use a different color for this, right? Somewhere in here, in this curve, I'm going to have a point C. Now, I identified that point right there as point C. The reason I picked that one is because the slope of the tangent line right here that's f prime of c, right? That slope right there equals f prime of c. And I try to pick a point where the slope of the blue line matches the slope of the red line. And there has to be a point in there somewhere, at least one. There might be many, but there has to be at least one point in there where the tangent line slope matches the slope of the secant line around it. Okay. Now you may ask, why must the function be differentiable here? Well, that would be a good question. Let me do another sketch like this with a non-differentiable function, and I'll show you why we can't guarantee it without differentiability. All right, if we take a look at this line, or this function, f of x here, we can see that f of x is definitely continuous on AB. But that little corner point there screws up the differentiability, right? So once again here, I have the point a comma f of a. And up here I have the point b f of b. Once again, the slope of my secant line here, right, this is f of b minus f of a over b minus a. Right? That's the slope of that line. Well, the problem is, because f isn't differentiable, in this particular drawing, I can't find a tangent, I can't find any point C in between a and b where the instantaneous slope, right, f prime of c, matches the slope of that red line, right? There's no point. That slope is not parallel, right? It's not the same slope. Over here is not the same slope. This point right here, this point where differentiability fails, is where I should have had a tangent line equal to that secant line slope, but I can't do it. Okay? So I need that shows why we need differentiability. Okay, that's it for today. We'll take a look at how this applies in class on Monday. I'll see you guys then. Have a great weekend. Talk to you guys later. 2 chains. Bye.